So my name is Carlos Trujillo. Lead data scientist at Wise. I don't know if you ever used the app or have ever transferred money abroad. This is one app of a finance app. And at the same time, I'm principal data science at PyMC Labs. If you ever use PyMC as a framework, PyMC also have like a consultancy side where all the writers of the packages that contribute in open source are able to as well, provide consulting. And yeah, I'm there as well. So today I want to talk a bit of statistical media mix modeling. But before of that, I also want to have a sense of the room. So I want to know how many of you are familiarized with regressions? Raise your hand. Nice. How many of you are familiarized with Bayesian modeling? Great. Okay, so I will not need so much introductions. And the final two questions, how many of you are familiarized with marketing? Okay. And what about causality or causal reasoning? The apparel theory? Yes. Nice. Great. So what I just want to quickly define right now is media mix models. And to put it in simple, media mix models are what I like to call a glorified regression model. So we are doing a more sophisticated regression model to understand what is the impact of certain drivers. Those drivers, as you can imagine, the media in part of the name, it's media advertising. So we do marketing media advertising, we spend money in certain channels, and we want to understand how much money are we getting back from what we spent. So that's the whole logic. And in order to do this, we apply these sophisticated regression models. Now, this is, let's say, the first layer. And this is interesting. We can do the math. But what I have been more interested in the recent years is about causal media mix models. And what the causal work brings right now is just a bit of additional structure. Because when you are building these models, you're actually interested in understand what is the impact of your intervention. So you are not only interested in understand what is the, probability of y given the data, given some x. You actually want to understand the probability of y given do x something. Once you intervene x, what will happen? That's the question. What is the causal impact of our spend? In the same time, the good thing of these models is that they are very interpretable. So usually every time that we do these models or these causal models, we can also write down these causal DAGs or direct acyclic graph, where we can basically also observe how our variables or our different nodes are related between themselves and against the target variable that we want to model. So I usually face a scenario during these days where we have these causal models that we spend a lot of time structuring and defining and running, and somehow they say something, let's say, oh, channel X worth $2 million, but then you do a simple A/B test or you do any type of experimentation, and all of a sudden you see that it should be actually like, 7 million or 5 million or whatever. So again, models can or are usually wrong, and sometimes you do experimentation and you know it. You actually do something in the world and you see that it's different from what the model interpreted at the beginning. And for that reason, we invent, or not invent, but we came up with an idea of calibration. And calibration, it's a very interesting idea, more in Bayesian models. In simple, we are just taking the likelihood from our model and we are appending a new observation that should be fitted in the process. So we are not already only fitting against our observations, we are adding an additional observations that should fit the contribution of a specific parameter. So we have, again, the parameters that estimates the value of x2, and we have an observation where those parameters should fit to make x2 have certain amount of contribution against the target, on top of the regular fitting, where we are trying to reduce the, the square errors against the total target, given the rest of the parameters. That's more or less in simple what you can see here. And we can do that because every time that we intervene in the world, we know our actions. We know how much spend did we spend extra, like 20, 30%. We know this delta. Usually, if the experiment is successful, you also know the delta of the outcome. So you increase 20%, and then you see 5% extra of new sales or users or whatever. And using these things, again, you can append these to the likelihood so we can get a calibrated posterior distribution. So this sounds very nice. And this, it's a very easy way to sell to your stakeholders or managers, because you go, you say like, oh, I will do some model, we will get some results, they probably will be wrong, but then we have experiments and we will append all of these experiments to the regression, and that's it. We have the perfect model that will always say the right answer. But what I want to say here, oh, and by the way, usually the information from the experiments, my bad, came from instruments like difference and difference, synthetic control groups, regression discontinuity, or regular randomized control trials like A/B tests. So you can get you can run any of those type of experiments, either observationals or control it, and then you can use the information from them to fit your regression. But sadly, and this is the point, and hopefully we go to it by the end of this presentation, calibration, it's not magic, it's just math. And that means that we need to treat it in that way. We can just append experiments indiscreetly and just expect to get some output. So I will just show you this in the Bayesian way. And what I mean in the Bayesian way is like, we will create, or I create a small set of data, or a simulated data set, where I generate in purpose some spend channels, I generate some noise and special events and some trend and contributions. And given all of that, I will create a target variable that then we will analyze. A small shout out here, I did this using PyTensor, which if you don't know is basically the backend of PyMC, and allows you to do a lot of very interesting things, more if you are trying to do graphical models or data generative processes. So in this case, as you can see here, I just create like 4 vectors, I give them some values, and then we have all the channels. I repeat the same thing for the components. And then I start to define the structure between those channels. So once we have all the parent nodes, all the things that we see before, I can start to define like how all of those variables relate. And again, I can define a graph, in this case, this graph that you see there, where we spent some money, that money generates some exposition, that exposition correlates with other channels, and we also have events like that one there that increase also the amount of exposition that we have against our users. You can imagine this like, I don't know, Christmas. So for sure in Christmas, either you spend or not, some more people will see you. All of these you can write it again in PyTensor, which is very handy because then you have the possibility to actually express this graphical model in PyTensor and print it, and just get an understanding actually of if what you are running or the more abstract model that you were writing here is actually what you did. So you can use, I don't know, functions like, I don't know, the py.print, and then you can see how all the variables are related. And if your more abstract representation is actually close to your more explicit graphical representation. So I don't know, if you have ever used PyTensor, this is just a small shout out that you should use it. We are contributing a lot, and it's a very nice tool if you are working with graphical models. But by the end of the day, if you repeat this process several times with several variables, we will get the target, which is this one, that will be representing this graphical DAG that we have there, this causal DAG, which at the same time will have the following underlying structural causal equation, which is the one that is under that. So this is our data. This is just for context. Now that we have our data, we want to run a model, a media mix model that you can build in PyMC with a few lines of code, defining your priors and a few other things, and then running it basically. So right now, if you want to use or you want to build media mix model, you can actually use PyMC marketing. This is just an out-of-the-box tool that we build inside of PyMC, and just defining the type of saturation or add stock effects that you want to observe, you can feed your model in, again, few lines of code. To give you also an introduction, in media mix models, we have these two main effects, which are add stock and saturation. Basically, saturation is talking about like the diminishing returns effect of a spend. So we spend more and more and more, but that spend is not returning the same amount of value as you move forward in X. And on the other side, you have the add stock, which is the lagging effect. I spent today, but because I was exposed to people a lot today, I will get some returns in the future, even if I don't spend in the future. So this we'll call it kind of the brand effect. So those two things will be in our model, and these are things that we also want to estimate from our marketing effects. We feed all of that. We get our PyMC model, or our Bayesian model is what we have there. We can also print it. Again, because all the library, like all PyMC itself, is a structural causal Bayesian modeling process, we can get a graphical representation of whatever that we are computing. So it's very important to understand that every time that we write, let's say, any PyMC model, we are writing a model of the world, a model that follows a specific structure, a model that follows a specific logic. We are not just writing a simple equation. That equation will have some meaning under it. And even if you don't know it, even if it's explicit or not, it's present. So we feed it, and as in any model, you will see, oh, my sampling is running properly. I don't see like any major problems. If you do some checks, you see, well, the feed is kind of okay-ish. I get some interpretation of the channel. So I don't know, X4 it's great, X1 is poor, X2 is also poor, and so on. And you are sort of happy. And if this model is true and their causal interpretations are true, then we can apply a lot of do calculus. So we can ask to the model, tell me what will happen if I condition certain variable to be different. And then I can start to compute the causal effect of that variable. So I can say, okay, let's try to understand the effect of X2. What is the causal impact of X2? So I can run and sample the posterior based on the parameters that I have and say, if X2 is equal to 0, tell me what happened. What will happen if X2 is different to 0? And the difference of that will be the effect, or let's say how many users you will be losing, okay, if X2 is 0. And we can compute that, again, in PyMC. We get the result, and we can observe the daily effect and the cumulative effect. This is what you will observe if you run, let's say, some synthetic control group, and you observe a counterfactual, and you compute the difference. That's more or less what, again, your counterfactual will tell you. If you have ever used, I don't know, causal impact from Google, maybe you're sort of familiarized with those pictures. So here we have the model interpretation of what should be the effect of X2 if we intervene, if we drop the channel to 0. For sure, you want to validate this information. In this case, the model is saying, like, if you drop that channel to 0, you lose like a user a day, and that will be like 10 users if you run it for several days. But what happens if we actually intervene? If we drop the channel to 0 and we compare, what we see is that our model was totally wrong. Our model at the beginning was estimating that we will lose something like 10 users, but when we reduce the spend to 0, we actually see a drop of 600 users. So the model was totally underrepresenting the value of X2. And this is where calibration goes to the rescue and says, well, if this happened, give me now your input from the experiment, let's append it to the likelihood, and let's try to now correct that error. And we can do that. Again, in PyMC marketing, we have a specific function that is called add lift test measurements. We can create a test. We can define, as I mentioned, how much is the delta of a spend that we have, how much is the delta in the observational delta in our target variable. And we can now, in this side, we will have to the parameters of the model, in this case, to the saturation parameters of the model, we will have a likelihood that he needs to satisfy on top of the likelihood of the regular rest of observations. So again, this is where Bayesian models becomes handy, because we can fit them again different type of observations, and we can fit like basically any of the parameters that we are defining against those. And the result of that, when we compare, is even worse. So we run this new model, we did the calibration, in theory it should be okay. We have some correction, like you can see that now the channel was steeper, like it's even moving close to the same direction as the initial way, but it's still like 10,000x run. And then this is where people go like side-talk here, and it's like, okay, so calibration doesn't work. Like, how can I get a model that is actually estimating properly my marketing spend or my marketing actions? And that's where causal theory pops in, because that's what can help us to identify what we need to do in order to get the right estimates. So if you have ever read the Perl theory, you will know that structural causal DAGs have different type of, again, structures, sorry, which are called chain, forks, and colliders. Based on the structure of your DAG, you need to define a specific type of regression, or you need to adjust for a specific type of channels, depending on the structures that you have there. And what happened is, like here in this DAG, this is how our data was generated, this is how our world works. We have a lot of different things that we need to control and need to take account for. One of those, and maybe even the most initial important one, is like every time that we run a diff and diff, AB, or any of the methods that I previously mentioned, you are estimating the total effect of your node. In the meantime, if you just run a simple regression and you put, let's say, x1, x3, and x4, you are trying to compute the direct effect of these channels. As you can see in the DAG, we have like the purple line where we have the direct effect of x2, but at the same time, x2 goes to x3 and x4, and that's an indirect effect. So every time that you measure, again, any contrafactual experiment, you're measuring the total. So not only the effect that goes through the purple, also the effect that it's go through the yellowish lines. And if you just compare it, like you are not comparing apples to apples, you're comparing, apples to other stuff. So two very different things. So that will never match, starting from there. On the other side, if you see this, when we run a multiple linear regression, we are not only observing the relation of one variables against the target, we are actually observing the conditional pairwise relationships. And that means that if I condition on x3, I'm also generating a spurious correlation between x2 and x1. And this happens because here in the DAG, we have a collider structure. We have x1 that goes to x3 and x2 that goes to x3 as well. That's basically a collider, again, if you have ever read about causal structures. And that will generate, again, in our model, a spurious correlation between x1 and x2. But that relationship doesn't exist. But the model will see it, because when you condition on x3, they relate. So if we want to observe the effect of x2, we cannot control for the total effect of x2. We cannot control also for x3. We actually should remove it from our regression model. And at the same time, we have some other confounders, like events, that if you don't account for events, then you will have a bias estimate as well of x2 over there. So all of these things are not, let's say, statistical questions, are more like causal questions. And if you just create models where you put, let's say, everything on the blender, which even if you don't believe it, this is very common these days, you just do regression, you don't think about causal relationships, you don't think about DAGs, you put everything on the blender and click run, then your estimates will be wrong. Now, if we follow Perl theory, we can say, okay, causal reasoning to the rescue. We can feed a model only on x2. We run this model because we know the causal structure, or we discover it. We will know that the effect of x2 will be isolated. We will not be blocking with any extra variable like x3 and x4. We will not be blocking the path of information. And by consequence, we could capture the total effect in that regression. And if so, that regression against our experiment should be close. And that's exactly what is happening. So now we have a regression that is built to capture the total effect of x2, and we did an experiment that will capture the total effect of x2, and those two are very close together. And we could make it closer if we apply experimentation on top of it, or if we now add another likelihood to our model to fit. So the insights that I hope that you get for this presentation is, even if you have a lot of experimentation and you want to apply this experimentation to your model to correct for those biases, like no amount of experimentation could, calibrate or make a model better if you are causally misspecifying it. You need to understand the different DAG structures. If not, then you will not be able to recover the true causal effect of each of those nodes. And on the other side, you need to understand that adjustment errors are like crucial. You maybe don't need a model that explains everything. Maybe you need several models where each one of those explains a certain part of reality. So one model explains x2, another model explains x3, and so on. So I think that pursue that single model that explains everything, it's also a very hard thing to do. If you want a deep dive, I will just share the notebook where you can see basically the whole process here. And if you just want to understand or read more about these topics, at WISE, at Bolt, and at PyMC, we are doing like a lot of content just to explain all of these things. So you can go there as well. And I think that that's it. So thank you for your time.
Thank you so much for the presentation. And we have a couple of questions. Please don't forget to use Slido for Q&A. So the first question is, how did you come up with the initial model?
How I came up with the initial model, if like in this example, I just built the initial model as an example of what do you do when you're like in a company. They give you a data set with 3 variables, and then you just need to figure it like, okay, what is the value of each of those? So you just plug everything in and run it. So that's a bit of what I wanted to show with the initial model. It's just an example of, well, you just run a model with whatever you have, plug everything and click run. So that's, okay.
And the next question is how to deal with bad, wrong data in my model?
Yeah, that's a very interesting question. So I will say, if you have like any piece of data that doesn't make sense to you, at least in causal terms, what you usually want to do is try to check the conditional dependence of your data. So let's say you want to understand which variables are dependent on each other or are dependent on others. If a variable is dependent on other, then you need to start to maybe account for it depending on the structure in your regression or not. So I'm not sure if it's like wrong data, but it's definitely a problem of what data you put into your model at the time of do regressions, and how do you decide which data goes there is through causal discovery. So that's something that you can also find out in my blog, how to do causal discovery with the different variables that you have.
Could you apply causal structured learning here without including your expert knowledge?
I think that you can do like you have a lot of algorithms out there. For example, if you go to DoY, or the guys that build DoY, you have something that is called greedy search, where you basically just plug your data in, and they will do a search over the node space over several different type of DAGs that could be plausible given your data. You could get some answers, so you don't need to put any expert knowledge. But I think that the expert knowledge is actually valuable because will help you, like the number of combinations that you can have with 4 or 5 variables in your dataset is almost like it's huge. So when you add a bit of expert knowledge, you basically cut the number of possibilities that are also like nonsensical. So maybe you have, I don't know, something that is saying that, oh, actually target, your target variable is driving your spend in Google, and like that's not true. So why you will explore that part of reality? You want to discard it with your expert knowledge. So add knowledge to your data. I think this is what brings meaning to it.
Do you have any book suggestions for understanding causality and the do calculus?
Yes. So in that sense, I would recommend the first one that I really like. It's Alexander Molak, Causal Discovery in Python. I can also give you the link. I will put the link in my notebook so you can have it there. You have you the apparel, the the why do why the I forgot the name, but it's the book of why. Sorry, the book of why from you the apparel. And also, Apparel have one that is even older, that is in early 2000s, I think the 1999 version. Um, it's causality for Python or something like that. So you can also take a look to that book. That's also interesting. It's more foundational, and then you can actually see if you read Judy Apparel, you can see how he went from Bayesian modeling to causal modeling because these two topics are like very related. And again, even if you don't know it, if you have ever write a model in PyMC, you write a causal model. I mean, maybe you know it or don't, but you did it. So that's a very important thing that again.
And we have one more question. Costs are dependent on the season, for example, Christmas. Should I include costs or just go with impressions as fourth input?
Yeah, that's a very good point. I will say impressions in marketing is basically exposition, which is closer to our target variable. And by consequence, the noise between impressions and the final target is usually less than if you just take a spend. Again, the amount of exposition that you get is not only depending on the spend, is depending on a lot of other factors that will add noise to that relationship against the target. So it's better to take variables that are closer to that part of the funnel than further. So impressions.
Okay, thank you. So with that, we can wrap up. We don't have any more questions. So a big thank you to the speaker and to the audience for questions.